In this video, we'll talk through the National 5 Chemistry Unit 2 topic of everyday consumer products. By the end of this video, you should be able to identify, name and draw straight-chained alcohols and carboxylic acids up to 8 carbons. You should also be able to explain trends in melting points, boiling points and solubility, be able to describe common uses of alcohols and carboxylic acids, and be able to complete neutralization reaction equations involving carboxylic acids. Starting off with the alcohols, also called alkanols. All alcohols will contain an OH group or a hydroxyl group. The hydroxyl group is its functional group. That's the part that you're looking for to confirm if you're dealing with an alcohol or not in questions. So looking at this compound here, it does have an OH group. That means we are dealing with an alcohol in this one. We can also be asked about saturation. So saturated alcohols will have carbon-to-carbon single bonds. There is the possibility of having an unsaturated alcohol that would have at least one carbon-to-carbon double bond. That's very unlikely. I don't think I've ever seen that come up at National 5, but just in case, it's just the same as with alkenes, having a carbon-to-carbon double bond and being unsaturated. If you're dealing with the most common types, the saturated alcohols, they have a general formula of CnH2n plus 2O or CnH2n plus 1 OH. When it comes to naming them, all alcohols end in OL, all with the O at the end. They are named similarly to the alkanes, but again, the ending is OL instead of ANE. Page 9 of the data booklet has some examples of the alcohols. So for the simplified names, you'd have things like methanol, ethanol, propanol, butanol, pentanol, hexanol, heptanol, and octanol, up to 8, which is how far you need to go. So then when it comes to naming these types of chemicals, if you're asked in a question to name these, the first thing you want to do, same as with the hydrocarbons, is you're looking for the longest chain of carbons. In this case, it's 2. And we can see from the data booklet that if it's got 2 carbons, that's going to start with eth. It's an alcohol, so we have got ethanol for this one. If you have an alcohol that has got more than 2 carbons, you will have different isomers. Isomers are when you have the same molecular formula, but a different structural formula. That means that you've got the same number of carbons, hydrogens and oxygens, but they're arranged differently. We want to, or need to, number where the hydroxyl group is, the OH group is. So if we look at some examples here, so the first one, we've got 5 carbons in a chain. Using the data booklet, we can see that for 5 carbons, if we've got 5 carbons, the answer is going to start with pent. The data booklet shows you some examples. Now, this doesn't tell us what 5 carbons for the pent ones is, but you can use the kind of naming arrangement to help us out. So it starts with the beginning, pent for us, AN, so pentan. Now we're looking at the number, and then we've got all. You've got dashes either side of the number. So looking back at our first one, well, the alcohol group, the OH group, is on the very end. That's in position 1. We have got pentan 1 all. Second one, we've moved it across a position. So instead of 1 all, we've got 2 all, so pentan 2 all. And the next one, we've got 3, so it's going to be pentan 3 all. In the same way as we did with the double bonds between the carbons, we want to have the smallest number that we can. We want to number from the end closest to the functional group. What I mean by that is, I don't know if I've got an example. Let's find an example. So let's say for talking's sake, I'm going to take this one here. I'm going to move the OH group over to the far side. That is still position 1 because we're now numbering from right to left. So position 1 is going to be this carbon here. So this would still be called pentan 1 all. So when I grab it, I'm going to tell this software to name it, then we've got pentan 1 all. So be careful with that. You still need to look at the side to identify what side you should start numbering from, and then it will hopefully fall into place for us, like so. We can also have alcohols with carbon branches. So if we look at this one here, first thing I want to do is look for the longest chain. The longest chain has to have the carbon that contains or has the OH sticking out of it. So this carbon here is my most important one. So 1, 2, 3, straight across the way. So we could be given a shortened structure formula like this. Something that might help you visualize what's going on is to expand it out and draw out the full structure formula, something like this. Our longest chain is 3. Now it could be the 3 through the middle, or it could be 2 and then up to the side. It will still be named the same as long as we pick the correct longest chain. So we've got propan. It's 1 all because the OH group's on the end carbon. Propan 1 all. We've got a branch off the second, and it's a methyl group because it's 1 carbon. So 2-methyl propan 1 all. And this is what you come up against as well with the double bonds, the alkenes as well, for that one. So drawing them out might help you kind of identify which side to start with, the counts, and all those things. But that's what we'd get for our answer there. moving off to another example. Again, let's make this the full structure fun with to maybe help us visualize what's going on. We have got 4 carbons in the longest chain. And that's an example we need to start from the right-hand side in terms of numbering. So we've got 1, 2, 3, and 4. The OH group is coming off the second. So that will be butan, 2-ol. I forgot to go back to here. So you can see but for 4 carbons in that one. So it's going to be butan, 2-ol. And we've also got the methyl group. The methyl group is coming off of the second as well. So 2-methyl butan, 2-ol. You can basically go the other way and from a name, start to draw it out. So what I do is I start with the but part. So I draw 4 carbons in a chain. I will have an OH group coming off the second carbon, and then a CH3 coming off of the second carbon as well. Now we'll look at the properties of alcohols. Alcohols are highly flammable substances, and as they get bigger in size, they become less and less flammable. As alcohols increase in size, their boiling points increase due to the increasing strength of the intermolecular forces. Intermolecular forces are the forces that exist between molecules. This also comes up in the hydrocarbons topic. We can see that if we go into the data booklet, and we can look at going from meth, eth, prop, and if we grab the next prop as well, if we grab the but as well, we can see the values are increasing. A little bit awkwardly, their melting points initially at the start, they're getting smaller, so becoming more negative, but then it starts going up and then down again. So with the alcohols, melting points, they're a bit uneven, a bit all over the place, so we don't kind of tend to look at them. What we can also be asked to do is compare the alcohols to their alkanes and alkenes counterparts. So if we look here, so if we compared methanol and methane, methanol has higher melting point and boiling point, and that's because they have stronger intermolecular forces. So we can use the data booklet to look at their melting points and boiling points. Higher melting points and boiling points mean stronger intermolecular forces. So just carefully check and compare the numbers that we're asked to do. When it comes to dissolving in water, their solubility decreases as their chain length increases. So as they get bigger and bigger and bigger, they are harder, more difficult to dissolve in water. Alcohols can be used as fuels, as they're highly flammable and burn with very clean flames. Alcohols are often used as solvents to help dissolve different chemicals, often used in cleaning products to help get rid of different materials off of surfaces. Next type of chemical is a carboxylic acid or alkanoic acid. These contain a COOH, the Q group, known as the carboxyl group, and it's the carboxyl groups, it's the functional group of carboxylic acids, and that's what we're going to be hunting for when we are dealing with them. If you look at the one on the left, that has only an OH group, that makes an alcohol, whereas on the right hand side we have this C double bond OOH or Q group, and that's going to make that a carboxylic acid. If it's a saturated carboxylic acid, so again that means single bonds between carbons, it will have a general formula of CnH2nO2. So for every 1 carbon, there's 2 hydrogens on it, which we can see there. Naming next. So all their names end in oic acid. Going back to the data booklet, we can see down the bottom there are 4 examples of the carboxylic acids, and we can use them to help us write the names. You then go up to pentanoic acid, hexanoic acid, heptanoic acid, and octanoic acid. Similarly named to the alkanes, the beginning, and then oic acid on the end. So looking at this one, we have got 3 carbons in the chain. It's got the carboxyl group. Data booklet helps us. 1, 2, 3, propanoic acid we've got for that. You will see here that I've drawn them out in 2 different arrangements. The first one is a nice 90-degree angle, which is really helpful in your jotter to help sit in a line and just look nice and neat and tidy in that. But in reality, because the atoms will push away and repel each other, they come more as this kind of angled format. You can draw them in any way, shape or form. I'm more leaning towards the one at the bottom. Easier on digitally, I can kind of adjust it as needed. But like I said, top one's quite good and jotters just looks a wee bit neater sometimes. For that one, we can also have branches like we did with the alcohols and other chemicals. So in this one here, again, let's puff it up to see all the bonds. We have got 1, 2, 3, 4 carbons in the longest chain. So I made this just straight through the middle. Has to include the one with the OH, so C double bond OOH or carboxyl group, which it does. We've then got a branch coming off of this second carbon. Branches are methyl groups. A 1 carbon branch is a methyl group. It's coming off the second. So 2-methyl butanoic acid would be an answer for that one. Okay, what are some of the properties that we need to know about? Similarly to the alcohols, as they increase in size, their boiling points increase due to the increase in strength of intermolecular forces. And we can see that from the data booklet. Their melting points, again, are a little bit more complicated because there's more chemistry going on than we really care about just now, where initially it's increasing, but then it goes down. Moving further along, we can compare them. If we compare them to, let's just do it to the alcohols, they will have higher melting points and boiling points than alcohols, and then also than the alkanes. Then, as I said, with alcohols, the stronger the intermolecular forces, the higher the melting points and boiling points. So you can use the values to help guide you there. Other properties of carboxylic acids is that the small ones are soluble in water. Their solubility in water decreases as chain length increases. They'll have a pH of less than 7 and behave like other acids. So they'll react with alkalis and bases, which we'll come on to shortly. Okay, so from Unit 1, acids and bases topic, acids can react with bases in neutralization reactions. Examples of bases include metal hydroxides, oxides, and carbonates, and also ammonia. Acid plus base makes salt and water. And if it's a carbonate, you'll make carbon dioxide as well. So that's a recap from Unit 1. We can be asked to work out the names of salts that involve an carboxylic acid being used. The name of the acid changes ever so slightly. So methanoic acid would provide you with a methanoate salt. Ethanoic becomes ethanoate. Propanoic becomes propanoate, and so on and so forth. You can be asked about metal hydroxides plus acid. That's going to make you use salt and water. So you could be asked to take two chemicals and work out what salt is going to be made. So the hydroxide is potassium. So the salt that's made is going to be potassium something. Methanoic becomes methanoate. So that will make potassium methanoate as your answer there. A metal oxide plus the acid makes you salt and water again. If you have sodium oxide and ethanoic acid, well, sodium oxide will give you the sodium. Ethanoic becomes ethanoate. So sodium, ethanoate, and water. And then the last type was with carbonates. And we need to be careful here that you also make carbon dioxide. So if it's calcium carbonate and propanoic acid, then it's going to be calcium propanoate, water, and carbon dioxide as well. So that's one of the things that ties in really tightly with the acids and bases from Unit 1. What are some uses of carboxylic acids? One of the most commonly used carboxylic acids is ethanoic acid. Ethanoic acid is found in vinegar. So vinegar is a solution of ethanoic acid, and it's used in household cleaning because it's a non-toxic acid. So it can be quite good to get rid of different stuck-on stains. It can be good for non-streakiness on window cleaning, things like that as well. Carboxylic acids are used in preservatives, increasing the shelf life of materials and products, soaps, and also medicines as well. Just a little recap on solutions. This is something that doesn't really fit into one particular topic, but here's as good a time as any. When a chemical dissolves in water, it's said to be soluble in water. If a chemical does not dissolve in water, it's said to be insoluble in water. Page 8 of the data booklet has a grid, a table of different materials and whether or not they dissolve in water. So VS, very soluble, S for soluble, and I for insoluble. So when you're dealing with making a salt, you can actually look and see if this thing can dissolve or not in water. If a chemical doesn't dissolve in water, it might dissolve in other things. So things like nail varnish, certain paints, stains, you might not be able to scrub them off with water. But if you use something like acetone, which is a nail varnish remover, some alcohols, they might be able to remove them and dissolve them away from the surface. Page 8, as I said, solubility is found there. The solute is the substance which is being dissolved. Solvent does the dissolving. In these examples, that water would be the solvent, and the solution is the mixture produced after dissolving. And that can come up in questions. Speaking of questions, here are some exam style questions now. The first one is talking about hand sanitizers used in many locations, like restaurants and hospitals. And the structure of the active ingredient in many hand sanitizers is this. So we have to name this compound. First thing is we have 3 carbons with the hydroxyl on position 2. We can see we've got 3 carbons, that's going to be prop. And there's 2 options it gives us here for prop, propan 1 or propan 2. Whereas our OH group's in the middle, that means we're going to have propan 2. Just as straightforward as those 4 carbons, are you going to get butane something. Okay, in this one we have got a lot of information in a passage. So they're talking about the little pen-tailed tree shrew found in the jungles of West Malaysia. Feeds on nectar from the Bertam palm tree, and the nectar contains glucose, which ferments, producing solutions of up to 3.8% alcohol. Therefore, the tree shrew regularly drinks a solution which is equivalent to a man drinking 9 units of alcohol per day. It seems that the tree shrew never gets drunk because it's able to break down the alcohol much quicker than humans can. The alcohol produced is ethanol. Draw the shortened structural formula for ethanol. I don't think we needed all that beginning bit just for that bit, but maybe we need it for the second part of the question. Okay, draw the shortened structure formula for ethanol. So what's ethanol? Ethanol is 2 carbons. Double check. 1, 2, yes. 2 carbons. It's an alcohol. Well, needs an OH group. So this is what the full structural formula that we've got here. And in a shortened structure formula, we want to take each carbon individually and write what it's attached to. So the first thing we've got is a CH3. We've then got a CH2 with an OH group. CH3, CH2, OH. Gets you that. So oftentimes it's easiest to just sketch out the full structure, and that makes it a wee bit easier to kind of visualize it. Some people, I can kind of draw them in my head so I can see, right, I need a CH3 and need a CH2 OH. But as I say, not worth taking the risk, I would say, in a test or an exam. Just a wee quick sketch, and then you should be able to get to the answer there. Okay, next part of it, we're asked to calculate the volume of alcohol solution the tree shrew drinks each day, and we are given a relationship to use. It tells us that the volume of alcohol solution is the units of alcohol times 1.25 over the percentage of alcohol. Now just narrows into the bit contains information we should care about. So the volume of alcohol equals the units of alcohol. Hunt for units, 9 units of alcohol. So it'll be 9 units of alcohol times 1.25 divided by what percentage does it give us? 3.8. So it's just finding information, take your calculator, type in the values, and we get to 2.96 centimetres cubed as our answer. So just find the information, plug it in, and then we'll get to our answer straightforwardly. In this next question, we're talking about butanol as it's drawn out for us. We'll get 4 carbons in a chain with an OH off the second. Draw an isomer of that. We want to have a same molecular formula but a different structural formula. One of the easiest things to do is just move the OH group. So instead of having 2-ol, make it 1-ol. The other things you can do is you can make it into a branched alcohol. Now, I was just checking there, does it say anything about straight chained or not? It doesn't. Some questions might ask you to draw one with a branch, not a branch. Here we've got the options of either or. So I'm going to put 3 carbons in the longest chain. I'm going to put a branch off the middle, and this would give us 2-methyl-propan 1-ol. Or what we could do is we could put the alcohol group off of the second as well. So 2-methyl-propan 2-ol would be another option. So the most common ways of doing it is 1, move the functional group if it's got one. So move it onto position A1 in this case, or make it a branch instead of a straight chained one for there. Be careful with moving the OH group, because if you put it on this one here, that would still be 2-ol, because we'd number from the right to get the answer there. So yeah, that would pick up the mark there. This one, we are now on to a carboxylic acid. How do I know that? Well, one, it says acid. Straightforward. It also has COOH, C double bond OOH. Name the functional group. The 2 functional groups we care about are the hydroxyl group, OH, and carboxyl, COOH. This is an acid. This has carboxyl group, or technically 2 carboxyl groups on either end of them. Just like that. And if it's only the OH, hydroxyl would be the answer. Here we're asked to find the carboxylic acid. We are looking for Q, C double bond OOH. A has it. B doesn't. B nearly does. B has C double bond OO, but we're missing a H off of this side. Not got the OH part, and then D is just an alcohol. So the correct answer here would be A for this one. So C double bond OOH is what we're looking for. This one's asking us about solutes, solvents, and solutions. The solute is dissolved, solvent does the dissolving, and solution is made. What it's asking for, describe the water. So vinegar can be made by dissolving ethanoic acid in water. Well, water is doing the dissolving, water is our solvent. And this next one, we're talking about a hippopotamus. A hippopotamus out of water can look as though it's bleeding. It releases a red protective fluid that acts as a natural sunscreen. Interesting. One key component of this secretion is hyposudoric acid, which helps shield the animal from UVB damage. Quite a complicated looking compound at the bottom. I can see some OH groups and some COOH groups, so hydroxyl and carboxyl groups. What's it going to ask us? Suggest a pH value for the hyposudoric acid. Well, we've got carboxyl groups, 2 of them if I'm looking correctly. Carboxylic acid. Acids have a pH less than 7, so any pH value less than 7. So you just pick a number 1, 2, 3, 4 or whatever it might be. But any value below 7 would pick up the mark for that one. It's then asking us to circle the hydroxyl group. Hydroxyl group is an OH group. And we're looking for this one here. I would steer clear of the C double bond OOH ones because they're part of the bigger carboxyl groups. So yeah, I get that's an OH and that's an OH. But that's part of, if I go back, that's part of the bigger carboxyl group. So that one there would pick up your mark as a hydroxyl group example. In this one, we have to explain why butanoic acid has a higher melting point than propanoic acid. Melting points are to do with forces of attraction between molecules or intermolecular forces. But means 4 carbons. Prop means 3. Butanoic acid is a larger molecule, more carbons, bigger, whatever you want to say. And that means it will have stronger intermolecular forces. And that's backed up by the numbers. -5 is a bigger number than -20. So it does have stronger intermolecular forces to lead to that higher melting point. Next one, we'll get 2 branched carboxylic acid molecules. They've given us the names for them, so they're kind of helping us out a little bit. Let's just try and make sense of them. So butanoic acid, because we've got 1, 2, 3, 4 carbons through the centre. 3-methyl, because of the third, which means this carbon here is number 1. And the next one, it's 4 again. So you can see butanoic acid stays the same. It's 2 1-carbon branches off the second and the third, 2,3-dimethyl butanoic acid. Draw the structure of 2,4-dimethyl pentanoic acid. Well, but was 4. Let's go back to here. If but is 4, pent is 5. So we want 5 carbons in the longest chain. It has to have a C double bond OOH like this one does. And it has to have 2 branches off the second and the fourth carbons, just like this. So let's walk you through it. We've got 1, 2, 3, 4, 5. Now I've went from left to right for not deliberately, I just did. So we've got position 1 over here. We've got a methyl group off the second and off the fourth. That gives you 2,4, dimethyl, and then pentanoic acid. You can have it flipped around. Looking back, I probably should have done it the other way around because this one already has the carboxyl group on the right, but whatever one works for you. Yeah, that would pick up the mark. And that one, it says draw the structure. It doesn't ask us for the full structure or formula or shortened. I've done a wee bit of a mix between them. If it did say full, you want to draw all the bonds that are shown, but it's given us a choice here. We can kind of pick which way we want to represent it. On question 10, they're giving us information about acids and bases again. So acid plus base makes salt and water. And then now there's a bit of new information that acids and bases can be classified as strong or weak. And the salts formed, if soluble, will have a pH that depends on the strength of the acid and bases used. So strong acid and strong base gives you neutral salt and water. Strong acid, weak base gives you acidic salt and water. Weak acid, strong base gives you alkaline salt and water. Okay, so the first part we've asked is if methanoic acid reacts with sodium hydroxide, name the salt formed. The first part of the name comes from the base. The second part comes from the acid. Methanoic, methanoate, ethanoic, ethanoate. So we've got sodium methanoate would be the one for that one. Yep, that makes sense. And then next we're asked to Predict the pH of the salt solution formed when hydrochloric acid reacts with ammonium hydroxide. So hydrochloric acid, you can see from the table, tells us that it's a strong acid. And ammonium hydroxide is a weak base. So we're looking for strong acid, weak base, which is the middle option. So we're up in this bit here. That means we're going to make an acidic salt. Spoke before, acidic salts will have a pH less than 7. And again, you just give them any value that's less than 7. So 6, 5, 4, 3, 2, or 1. Okay, so by the end of this video, you should now be more confident in identifying, naming, and drawing alcohols and carboxylic acids up to 8 carbons, explaining the trends in melting points and boiling points and solubility, be able to describe common uses of alcohols and carboxylic acids, and completing neutralization reaction equations involving carboxylic acids. Thanks for watching. Goodbye.